Hi class. In this lecture we want to continue our study of applications of integration by moving in and talking about moments, centers, mass, and centroids. Now there's going to be a lot of definitions in here and only a little bit of calculus at the end, but especially if you haven't taken a physics class before or are still in a physics class, a lot of this stuff right here will be a good refresher. Okay, so a bunch of objectives. So we want to understand the definition of mass. We want to find the center of mass in a one-dimensional system. We want to find the center of mass in a two-dimensional system. We want to find the center of mass in a planar lamina. And then we want to use the theorem of Pappus to find the volume of a solid of revolution. And what this last one does is it's just another way of finding the volume of a solid of revolution instead of using the calculus or the integration method we've talked about prior. You could use this, but it's a good way to just see it now, but you should still, with your homework and everything, do the other ways you have learned. Okay, so let's start with mass. So several important implications of integration are related to mass. Okay, so mass we know is the measure of a body's resistance to change in motion and is independent of a particular gravitational system in which the body is located. Okay. However, because so many applications involve mass occur on Earth's surface, obviously, the object mass is sometimes equated with its weight, but this is not technically correct. Weight is a type of force and as such is dependent upon gravity. So force and mass are related by this following equation. So we know force on an object is equal to mass times acceleration. Okay, so you can solve for any of these, like for example, mass is equal to force divided by acceleration, or acceleration is equal to force divided by mass, and so on. All right, so the table here, I won't go through it, lists some commonly used measures of mass and force together with their conversion factors here. And so you can kind of see, things like a slug. A slug is equal to basically pounds divided by feet divided by seconds squared. And we've talked about some of these other ones in previous lectures. Okay, some conversions here for you as well. Okay, so let's talk about finding the mass in slugs. So going back, how you would define a slug, okay? A slug would be equal to pound divided by feet divided by seconds squared, okay? So find the mass in slug of an object whose weight at sea level is 1 pound. Okay, so let's do that. So we're going to use 32 feet per second as the acceleration due to gravity, right? So mass is equal to force divided by acceleration. So we have 1 pound divided by, because that's what we're trying to find, 1 pound, 32 feet per second, okay? So pound and then divided by foot per second, so going back, pound divided by feet per second, as I said there. Okay, see the per second, like as I showed. So 1 pound divided by 32 gets you this. And then this right here we know is equal to a slug based on that definition I gave. Okay, so because many applications involving mass occur on Earth's surface, the amount of mass is called a pound mass. All right, let's talk about center of mass in a one-dimensional system now. So you will now consider two types of moments of a mass. Okay, so we're going to define what a moment is now. The moment about a point and the moment about a line. To define these two moments, consider an idealized situation in which mass m is connected at a point. If x is the distance between this point and mass, okay, so we're connecting the mass to a point, and another point p, okay, then the moment of m about point p, so the mass is connected to some point p, okay, the moment is equal to m times x, okay, and what's going on here is that the moment of m, and x is the length of the moment arm. So let me kind of show an example of this. Okay, so the concept of moment can be determined simply by a seesaw. Okay, so we have this figure here that shows it. A child of mass of 20 kilograms sits 2 meters to the left of the fulcrum P. So the fulcrum P is kind of like the center point here. And an older child of mass 30 kilograms sits 2 meters to the right of P. All right, so from experience, you know that the seesaw will begin to rotate clockwise. Okay, moving the larger child down, right? So like the larger child pushes the other child up. So this rotation occurs because the moment produced by the child to the left is less than the moment produced by the child on the right. So remember how we define moment. It's m mass times x. Okay, so remember x going back here is the length of the moment arm. Okay. So the moment occurs because the rotation occurs because the moment produced by the child on the left is less than the moment produced by the child on the right. So the left moment here, you take the mass times the distance from the fulcrum, which is 2. So you'd have 20 times 2, which is 40 kilogram meters. And then the moment on the right with the heavier child, their mass was 30 times their distance from the fulcrum, 2. So 30 times 2 gets you 60 kilogram meters. Okay, so to balance the seesaw, the two moments must be equal, which they're not. For example, the larger child moved the position 4/3 meters from the fulcrum, okay, moved it in, then the seesaw would balance, okay, because each child would produce a moment of 40 kilograms. So this is how you could balance it. Like you could move the child in the right closer to the center, okay, to the fulcrum, and then that way you would have a balance in the moments, and then the seesaw would balance. All right, you can introduce a coordinate line on which the origin corresponds to the fulcrum, all right, as shown in this figure below. Okay, several point masses are located along this x-axis, so the fulcrum occurs at the origin of this line, or 0. Okay, the measure of the tendency of this system, okay, to rotate about the origin is what's called the moment about the origin, and it is defined as the sum of the n products, so the individual masses times the corresponding xi. Now, mi is the corresponding mass, and xi is the distance from the fulcrum. So it turns out if you sum their products, okay, so you're taking the mass times the distance here, if that sums to 0, then the system is in equilibrium, so it's equally balanced. All right, so the moment about the origin is denoted m sub 0 and can be written as the following. So the moment about the origin is just the sum of those products. All right, and so as I said, if m sum 0, if that sum is equal to 0, then the system is in equilibrium. Okay, so for a system that is not in equilibrium, though, what happens is the center of mass is defined as the point x bar, okay, at which the fulcrum could be relocated to obtain equilibrium. So where would I have to move the fulcrum to get equilibrium? Okay, that would be the center of mass. If the system were translated x bar units, then each coordinate x sub I would become x sub I minus x bar, because you're just moving it. And because the moment of the translated system is 0 now, we would have the following. So if you were to sum up each mass times their position minus the center of mass, well, you can just see through some simple algebra here, then that would just be equal to 0. So solving for x bar in this case, all right, you would get the following. The center of mass, remember that's what x bar is. Okay, the center of mass is defined as the sum of each mass times their corresponding distance from the fulcrum. So that's the moment of the system about the origin. And you would divide that by the sum of the mi's, or the total mass of the system. Okay. So when this total mass of the system, or excuse me, when the moment of the system about the origin is equal to 0, so that's when the numerator is equal to 0, we say this system is in equilibrium. Okay, so just some definitions here, just so we'll get back to this. So this is about moment and the center of mass in a one-dimensional system. So let's let point masses m1, m2, all the way to mn be located at x1, x2, all the way to xn. So the moment about the origin, m sum 0, is just each corresponding mass times their corresponding location values from the fulcrum. Okay, so just m1 times x1 plus all the way to mn times xn. And then the center of mass, which is denoted as x bar, is equal to the moment about the origin divided by the sum of the total masses. Okay, where that m without a subscripted value in the denominator there is just the sum of the masses. Okay, let's do an example. So let's find the center of mass of the linear system shown below. So the center of mass is this. Okay, so we're going to need this right here. So to find this, we're going to have to find the moment about the origin, just so we're clear. Okay, so the moment about the origin is the following. So you see M sub 0 is m1 times x1 plus m2 times x2, and all the way to m4 times x4. So look here, this has mass 10, its x value is minus 5. This has mass 15, its x value is 0. This is mass 5, its x value is 4. This is mass 10, its x value is 7. So just multiplying here and summing, the moment about the origin here, that m sub 0 is equal to 40. Okay, now we can figure out what the total mass of the system is. So that's this mass plus this mass plus this mass plus this mass. Well, you see that that is also 40. So the center of mass here, x bar, is equal to m0 divided by the total mass. So it's equal to 1. So note that the point masses will be in equilibrium when the fulcrum is located at x is equal to 1. So if we were to put the fulcrum right here at x is equal to 1, okay, then the center of mass would be in equilibrium. Okay, so then rather than defining the moment of mass, you could define the moment of a force now. So in this context, the center of mass is called the center of gravity. So consider a system of point masses m1, m2, mm that is located again at x1, x2, all the way to xn. Well then, because force is equal to mass times acceleration, then the total force would be m1 times a plus m2 times a plus all the way to mn times a, which would just be equal to the total mass, okay, that's what m is, times a, the acceleration. All right, so the torque moment about the origin, so we denote as T sub 0, is equal to m1 times a times x1 plus m2 times a plus x2, and so on. So just pulling this out here, this is just equal to m0, okay, which is, going back just so we're clear, m0 is right here, the moment about the origin, times the acceleration, and then by extension the center of gravity is equal to torque divided by force, which is the same thing as x bar. So going back, remember what x bar is. X bar is the center of mass. Okay, so the center of gravity and the center of mass actually have the same exact location. All right, let's talk about center of mass in a two-dimensional system now. All right, so you can extend the concept of moment to two-dimensional by considering a system of masses located in the xy plane at the following points. So now my center of masses, or excuse me, my masses aren't just on like a number line here, they're actually in the Cartesian plane, right, with xy coordinates. So rather than defining a single moment with respect to the origin, two moments are defined, okay, one with respect to the x-axis and one with respect to the y-axis, okay. So we denote those, as you can see over here, with respect to the m-axis here, that would be m sub x, that's the moment with respect to x, and m sub y is the moment with respect to the y-axis. So just some quick definitions here. All right, so we have, let the point masses m1 all the way to mn be located at the following corresponding points in the Cartesian plane. Well, then the moment about the y-axis, okay, so note here what's a little different, okay, the moment of y is equal to the mass times the x values, okay, so it works the opposite way you would think, and then the moment about the x-axis is the masses times the corresponding y values, okay, these work the opposite way you would think. So the center of mass, x bar comma y bar, or center of gravity, is x bar is equal to the moment of y divided by m, and y bar is equal to the moment of x divided by m, okay? And this is where m is the total mass of the system. All right, so the moment of a system of masses in the plane can be taken about any horizontal or vertical line. In general, the moment about a line is the sum of the product of the masses and the directed distances from the points to the line. Okay, so the moment here, another way here, about a horizontal line, instead of the y-axis, y is equal to b, all you're doing is taking your y sub 1 values and minusing whatever the horizontal line is by shifting it. All right, again, along the vertical line, x is equal to a, you're doing the same thing. You're taking your x1 and subtracting a before multiplying it by a moment there, or before multiplying it by the mass. Excuse me. All right, so let's take this. Let's find the center of mass of a system of point masses. So we got M1 over here has a mass of 6. M2 has a mass of 3 right here. M3 has a mass of 2. And M4 has a mass of 9. And there are their corresponding coordinates. Okay, so let's first off find the total mass of the system. So the total mass of the system, just adding up the masses, is 20. So M sub y. So you're taking the M1. So let's find M1. Where are you? Right here. To remember, for My, you're taking it. So you're taking the mass and multiplying it, remember, by the opposite way you would think. So by the x value, 3. Then you're taking 3, multiplying by the x value is 0. Then you're taking 2, multiplying it by the x value of minus 5. So the moment, and you do the same thing with 9. So the moment about the y-axis is 44. Do the same thing for the x-axis. Okay, sorry about that. You're going to take the corresponding mass, but the moment about the x-axis works the opposite way you would think. Multiply by the y value. Do that for each mass, and you get 12. So x bar here is the moment of y divided by the total mass, which would be 44 divided by 20, which gets you 11/5. And y bar here would be the moment around the x-axis divided by the total mass, which would be 12 divided by 20, which gets you 3/5. All right, so what this is telling us then is that the center of mass of this system is x bar comma y bar, so it would be 11/5 comma 3/5. So going back, 11/5 is a little bit more than 2, 3/5 is kind of around here. So the center of mass of this system is actually right here. Okay, right here where my mouse is. All right, so let's next move on to talk about the center of mass in a planar lamina. All right, so consider a thin, flat plate of material. This is important, of consistent density. This is called a planar lamina, as you see in the figure here in the PowerPoint slides. So density here is a measure of mass per unit of volume, such as grams per cubic centimeter. So for planar laminas, however, density is considered to be a measure of mass per unit of the area. So density here is denoted by this Greek letter, okay, which is the lowercase Greek letter rho, okay. So consider an irregular shaped planar lamina of uniform density P. So remember, uniform density P. Okay, bounded by the graphs given by y is equal to f of x up here, and y, and the other one, y is equal to g of x down here, somewhere between A and B. Then obviously the mass of the region, okay, the mass is equal to density times area. Well, we know the area of this area right here. How to find this? Well, you just integrate from A to B, the top graph minus the bottom graph with respect to x, and just multiply it by that value P, whatever the density is. Okay, so that's just how you get the rho times A. Okay, to get where the A is that area of the region you found with some very, very simple integration. Okay, so then going forward, to find the center of mass of this, partition the interval A to B into n subintervals of equal width delta x. Let x sub I be the center of the ith subinterval. So you can approximate the portion of the lamina laying in the ith subinterval by a rectangle, obviously whose height is the difference of those two functions. And because the density of the rectangle is rho, then its mass is equal to density times area. Well, density, you can see where this is going, is that rho times the height times the width. Well, you can see where this is going with integration. Now consider the mass to be located at the center of each subinterval of this rectangle. All right, the directed distance of the x-axis to xi, yi is equal to f of x sub I plus g of x sub I divided by 2. Obviously, so the moment of m sub I about this x-axis is the following. The moment, mass times distance. Mass, we know, right, going back, this is our mass right here. So just plugging that right in there. And then this y sub I comes from right here, which is f of x sub I plus g of x sub I divided by 2. So then following here, just with some simple calculus, always hang on to these formulas, okay? This is for the moments and center of mass of a planar lamina. If f and g, let's let f and g be continuous functions, that f of x is greater than g of x on that interval a to b. And consider the planar lamina of, again, uniform density bounded by the graphs of y is equal to f of x and y is equal to g of x on that interval. Then the moments about the x and y axis are the following. So the moment of x is equal to the density times the integral from a to b, and then in parentheses of f of x plus g of x divided by 2 times f of x minus g of x dx. Now the moment about y-axis is equal to the density divided by, or multiplied by, the integral from a to b. Now, this one's a little different. It's just x times f of x minus g of x dx. So then by extension, the center of mass, x bar, y bar, is given by the following. Once you find the moment about the y-axis, x bar is equal to the moment about the y-axis divided by the mass, and y bar is equal to the moment about the x-axis divided by the mass. Okay. In this mass, where mass is equal to, you take the density, multiply it by the integral from a to b of f of x minus g of x dx, right there. I know this seems crazy, but all you have to do is just have the formulas handy and follow the formulas. Follow the formulas. Okay, so let's do an example here. So find the center of mass, all right, of this lamina of uniform density rho bounded by the graph of f of x is equal to 4 minus x squared and x-axis. So I want to find the center of mass. So this is what I want to find, the center of mass. So to be able to find the center of mass, x bar, y bar, I need to find this integral, and this integral. Okay, so because the center of mass lies on the axis of symmetry, okay, right off the bat we know x bar is equal to 0. Moreover, the mass of the lamina here, the mass just following, going back, just following this integral right here. You're just going to take rho, whatever the density of it is. They're just giving it as rho, so you don't need to actually put a number in. You're going to integrate. You look where this graph crosses or is bounded by the x-axis. Obviously, that's from -2 to 2. So you're going to integrate from -2 to 2 over 4 minus x squared dx. You should get the following, and then that just simplifies to 32/3 rho. So to find the moment about the y-axis, a little bit harder. All right, place a representative rectangle in the region shown here. The distance from the x-axis to the center of that rectangle is that y sub I. So that's equal to f of x divided by 2, which is 4 minus x squared divided by 2. So because the mass of the representative rectangle is the following here, rho times f of x times delta x, you have the following. The moment about the x-axis is rho times the integral from -2 to 2, 4 minus x squared over 2 times 4 minus x squared dx. And you can simplify this very easily. I won't break through this because this is just some simple power rule integration. And you should get 256 rho divided by 15. So that's telling me y bar here is the moment centered around the x-axis divided by the mass, which is this, which just simplifies to 8/5. So the center of mass, the balancing point of this lamina right here is 0, 8/5 as shown in this figure. So think about that pencil balancing that center there. Okay, so the center of mass of a lamina of uniform density depends only on the shape of the lamina and not on its density. For this reason, the point here is sometimes called the center of mass of the region in the plane, or the centroid of the region. In other words, to find the centroid of a region in the plane, you can simply assume that the region has a constant density of rho is equal to 1 and compute the corresponding centers of mass. So as you saw here, what happens is the rho's cancel out. All right, so to find the centroid, just assume that the rho, the density is 1. All right, let's end by talking about the theorem of Pappus. So the theorem of Pappus, so this helps us find the solid of revolution, the volume of a solid of revolution. But anyways, let R be the region in a plane, and let L be the line in the same plane such that L does not intersect the interior of R, okay? This is going to be kind of like a donut shape. So as shown in this figure below, all right? R is the distance between the centroid, all right, of this region R and the line. Then the volume V of the solid of revolution formed by revolving R about the line, okay? The volume is equal to 2 pi R times A, the area, all right, where A is the area of R. Note that 2 pi R is the distance traveled by the centroid as the region is revolved about the line. All right, so the theorem of Pappus can be used to find the volume of a torus as shown in the next example. So we know a torus is a donut-shaped solid formed by revolving a circular region about a line that lies in the same plane as the circle. So you can use this now if you ever need to find a solid of revolution for this type of shape specifically. All right, so find the volume of the torus shown in the figure below, which was formed by revolving the circular region bounded by this equation. Okay, the circle x minus 2 quantity squared plus y squared is equal to 1, and we're revolving about the y-axis, okay? So my radius here is 2 to the center, and I'm going to take this and revolve it around. So you can see that the center of the circular region is 2, 0 right here. So the distance between the centroid and the axis of revolution, that distance, that radius is equal to 2. So because the area of the circle of the region is area is equal to pi, okay, then the volume, because it's pi r squared here, the volume of this torus is equal to 2 pi r a. So the area here is equal to pi. So it's 2 pi times 2 pi, which is just 4 pi squared. All right, which is roughly 39.5. So I know there was a lot in this to take forward, but the key thing here is to just slow down, remember your formulas, and go from there. And whenever you see a problem, find the corresponding formula.